GATE ECE 2026. Consider carrier transport in a Zener diode in the breakdown region, which is the dominant transport mechanism for current flow in this case. There are 4 transport mechanisms given, like drift, diffusion, tunneling, and ballistic transport. We need to identify dominant transport mechanism which is taking place in Zener diode under breakdown condition. First, let us check with the drift current. Drift current is taking place when we apply electrical voltage across the material or device. Here, the charge carriers are accelerated from one end of the device to other end due to externally applied voltage. This drift current normally dominant under reverse bias, but not in the breakdown region. So option A is incorrect. Now let us check with option B. Option B says that diffusion current. Here diffusion current means the charge carriers move from higher concentration to lower concentration, for which we need not apply any force for the charge carriers to move. So in this case, if we consider, the diffusion current occurs mainly in the forward bias condition. So under forward bias condition, diffusion current dominates. Under reverse bias current, drift current dominates. Now let us try to identify the reason behind this. So if we say forward bias means the positive end of the battery is connected to positive terminal of the PN diode, and negative terminal of the battery is connected to negative terminal of the PN diode. Nothing but P-type and N-type materials are connected to positive terminal and negative terminal of the batteries. So because of this, the charge carriers are forced to cross the junction where width of the depletion region is very, very small. Now under this situation, majority charge carriers in the P region are crossing into N region, where it becomes minority, because in N region, majority carriers are electrons. Now holes are entering into the device. Normally holes are less in number in the case of N-type. So once they cross the junction, they start to diffuse through the material and contributing the diffusion current in the forward bias. Coming to reverse bias, where negative terminal of the battery is connected to P-type material, while positive terminal of the battery is connected to N-type material of the device. Now in this situation, this negative terminal attracts the positive charge carriers away from the junction. Similarly, positive terminal of the battery attracts majority carriers, electrons in the material, towards positive terminal of the battery. So naturally, width of the depletion region is very, very wide. So the chances of majority carriers crossing the junction becomes very, very small. We can say close to 0. Now in this situation, the minority carriers in the P region gets repelled by negative terminal of the battery. Similarly, minority charge carriers holes in the N region gets repelled by positive terminal of the battery. So now minority carriers crossing the junction and contribute the current. This current is nothing but drift current. We will see the current, how much is contributed by each of the diffusion and the drift mechanisms. If you consider the particle flow here, it is contributed by hole diffusion. The first one denotes hole diffusion. The second one denotes hole drift. The third one represents electron diffusion. And the fourth one represents electron drift. So here, hole diffusion is taking place from P region into N region. Here, the second one, hole drift, is taking place from P region towards the opposite direction. So here, hole diffusion and hole drift are equal in magnitude but opposite in direction. So this hole diffusion and hole drift cancels each other. So net current is 0. The same logic is applicable for electron diffusion as well as electron drift. While electrons are diffusing from N region into P region, the holes, the electrons are drifted from N region, P region into N region. Here also, the amount of electron diffusion and amount of electron drift are equal. So they cancel each other. The net current becomes 0. So in no bias condition, the net current equals 0, because the diffusion current and the drift current due to holes and the electrons are equal. Now coming to forward bias case, where majority charge carriers are crossing the junction, Hence, the diffusion current becomes large. In the same way, electrons are crossing the junction, they are contributing the large amount of electron diffusion current. However, if we consider the hole which are drifted from N region into P region, means it is less when compared to hole diffusion. So hole drift is large when compared to hole diffusion. So there is a net current flowing in the device which is large in quantity. In the same way, if we observe with reverse bias case, where the amount of charge carriers crossing the junction is very small when compared to charge carriers drifting. So here, when compared to diffusion, I mean due to hole, the amount of drifting current due to hole is large. So even in the reverse bias, current flows due to drifting mechanism. So from this, we can conclude that under forward bias, diffusion carrier transport mechanism dominates, while under reverse bias, the drift current carrying mechanism dominates. Now the question is not about forward bias or reverse bias, it is about the breakdown region. So here, if you consider Zener diode, in Zener diode, the region near the junction is heavily doped, which is about 10 to the power 18 to 10 to the power 19 atoms per centimeter cube. So if you compare with the PN junction diode, it is 1000 times higher. Because of this reason, the Zener diode depletion region width is very, very thin. It is about 0.1 micrometer to 10 nanometer. Because of the strong electric field we apply for the material, the thin depletion region allows the charge carriers to tunnel through the junction. So here, under breakdown region, the current tunneling is taking place by the electrons and holes from one side of the junction to the other side. So if you can observe from this diagram, here electrons are tunneling from N region into P region. So in Zener diode under breakdown region, tunneling current is the dominant carrier transport mechanism. So option C is correct. This can be better visualized with the help of another diagram. If you can see, the electrons pass directly through the depletion region instead of surpassing the barrier, because we apply only a potential which is less when compared to the barrier potential. Even though the external force is small, because the depletion region is thin, electron tunneling is taking place in the Zener diode. Now coming to the fourth option, ballistic transport. Ballistic transport means the movement of charge carriers in a smooth and scattering free mechanism. Here, the length, that means distance between source and drain region of a device, is very, very short. Under this situation, the charge carriers, instead of going with the scattering, they have constant momentum, and also they go in a straight line. So unlike diffusive transport, which is taking place in many of the ordinary devices like PN junction diode or Zener diode, where diffusive transport is taking place and the charge carrier movement is random, they are colliding with each other. In the case of Zener diode, diffusive transport mechanism is taking place, not ballistic transport. This ballistic transport takes place only in ultra short nanoscale transistors and clean carbon nanotubes or graphene based devices. So ballistic transport is an incorrect option. Option D, C is the correct one. Thank you.